Hello and welcome to this video where today we're going to be looking at the power and energy in a circuit. So when you were at GCSE you learned that the power of anything was basically the amount of energy that's transferred per second. In other words, if we know the amount of energy, which is measured in joules, and we know the time, which is measured in seconds, then we can work out the power, which is measured in watts. And because watts are equal to joules per second, we just say that 1 watt is basically the same as 1 joule per second. So if we have 1 joule of energy per second being transferred, we say that the power of whatever it is that's doing that, making that energy be transferred, is 1 watt. Now that's all well and good, but when it comes to circuits, if we want to know the power, for example, that's given to this component over here, we'd have to measure how much energy it got in a certain amount of time. But that's very difficult. It's very difficult to measure the amount of energy that this thing actually gets in terms of electrical energy. So what we can do is we can go back to our basics in a circuit, and we can look at the potential difference and the current associated with this particular component. So if we go back to the equations that we had right at the very beginning, we've got potential difference defined as the amount of work done per unit charge, and work done and energy are essentially the same thing. So they're exactly the same thing. And we also know that current is equal to the rate of flow of charge. In other words, it's charge divided by time. So if we look at these, we can take these equations and plug them into here and work out what power is in terms of the potential difference and the current. So if we rearrange this, then the energy, or the work done, is simply equal to the potential difference times the charge, and then we've got the time in this equation. So if we rearrange this to get T, so the time is equal to Q divided by I. If we then take this and plug it into this equation here, so we'll put these two together, we end up with the power equal to the energy. Well, the energy is the work done, so that's VQ, divided by the time. So it's divided by this, divided by Q over I. So we're dividing by a fraction. And if you remember back to your primary school maths, if we divide by a fraction, that's exactly the same thing as multiplying by the fraction when it's flipped upside down. In other words, this. So we end up with this equation, VQI divided by Q. So we've got Q on the top, Q on the bottom, so they cancel out. So in the end, we end up with power simply being equal to V times I. Just change it around a little bit, so we have IV. In other words, the power of this particular component, so in other words, how much energy this transfers per second, is simply equal to the current which goes through it, which is this, multiplied by the potential difference across it if we had a voltmeter. And we could do the same for this. We could also do the same for the battery. So if we put a voltmeter across the battery, we could work out the total potential difference being supplied to the circuit, and we could measure the current going through, but basically by using this ammeter, going through the battery, and that would tell us the total amount of power that's being given through the circuit. So dependent upon where we put our voltmeter, tells us basically whether it's the power being supplied to the circuit when it's around this thing here, or whether it's the power of these components in this particular bit here. And as you can imagine, using conservation of energy, the amount of power you supply, or that is supplied by the cell or by the battery, is equal to the amount of power that's used up. So the power of this thing and this thing add up to the power that's supplied in the circuit. So let's have a look at that in a very simple problem. So we've got this circuit here. The current is measured by this ammeter here. So this ammeter measures 2 amps. So that's that there. The potential difference across the battery, so that's this here, is 9 volts. So we've got a potential difference of 9 volts being supplied to the circuit, and the potential difference across this resistor here is 4 volts. So this voltmeter says 4 volts. I want to find first of all the power supplied to the battery. So power equals current times potential difference, as we've just seen. So the current going through this battery is 2 amps. Multiply the potential difference across this battery. Well, this voltmeter reads 9 volts, so 2 amps times 9 volts gives me 2 times 9 gives me 18, and it's a power, so 18 watts. In other words, this battery is supplying 18 joules of energy every second to this circuit. So that's part A. So that was part A there. Part B. I now want to find the power supplied to this resistor here with the voltmeter across it. And basically I just do the same thing. So power equals current times potential difference again. The current's still 2 amps times by the potential difference. Now the potential difference just across here is 4. It's not 9. That's across the battery. This is 4. 2 times 4 equals 8. So I've got a power of 8 watts. So 18 watts is being supplied by the battery altogether, and this particular resistor is using 8 watts of that power up. It's transforming 8 joules of energy into, for example, heat per second. So part C, I want the power supplied to the second resistor. Well, if 18 watts is being supplied to the circuit, and this one here uses 8 watts of energy, then whatever is left over must be used by the other one. So it's simply 18 minus 8, so I end up with 10 watts. So this particular resistor has a power of 8 watts, and this particular resistor has a power of 10 watts. So this resistor is transforming more energy than this one per second. So that's basically how we use that very simple equation. Now there are some other equations that come in perhaps a little bit more useful, because if we actually go back to this thing here, not only could we measure the potential difference and the current, it may well be that we don't know the potential difference across here, but we do know the resistance. So we can get equations for power that have resistance in them. So again, if we start with our basic equation now, so P equals IV, so current times potential difference again. I also know from Ohm's law that V equals I times R, where R is our resistance. So I could take this and I can plug it into here, and I can do it in a number of different ways. So first of all, we'll just take this, and wherever I see a V in this equation, I'll replace it with V from here, but V is equal to I times R. So equation number 1, P equals I times V. V is equal to I times R. So I just substitute that in, and I end up with this equation here, I squared R, like that. So that's my first equation. So if I knew the current and the resistance of a component, then I can work out the power of that simply by doing the current squared times by the resistance. So that's our first equation. Second equation, we can do exactly the same thing, but I can rearrange this. So I equals V over R this time, and instead of replacing the V, I can replace the I. So P equals I, well, I is V over R. It's V over R multiplied by the V, and if we simplify that, we get V squared over R. So my second equation, P equals V squared over R. So if I know the potential difference across a component and its resistance, then I can calculate the power. Now, the third thing I can do, the very, very last thing, is if I go back to our definition for power, which is P equals E over T, so the energy divided by time. Sometimes I don't want to know the power, sometimes I want to know the energy. So if I want to know the energy, then all I have to do is basically work out the power and multiply it by however long the component is on for. So if it's on for 60 seconds, for example, if I work out the power of this to be, for example, 10 watts, and I know it's on for 60 seconds, then it's using 10 watts every second. So therefore, 10 joule, yeah, so 10 joule, it has a power of 10 watts, so it's using 10 joules every second. So over 60 seconds, it's using 10 times 60, so it's using a grand total of 600 joules. So if I want to know the energy, I just do the power multiplied by the time when the time's in seconds. So let's do a really, really simple example. I've got a 20 watt car headlamp. It's connected to a 10 volt car battery. Now this is a bit of a made up situation. Car batteries are normally 12 volts, but it'll show us how to use these equations. I want to know how much energy this headlamp converts into light in 3 hours. So I don't actually have to use any, I don't know the current or the potential difference. Well, I know the potential difference, but I don't know the current, for example, or the resistance. So, but I can go back to this. So we saw that power equals energy divided by time. So energy is power times time. I know the power and I know the time. I just have to be very careful because in this case the power is 20 watts, so that's fine. Multiplied by the time. Now the time's 3 hours. I don't want time to be in hours, I need it to be in seconds. So 3 hours is 3 times 60, gives me in minutes, times by another 60, gives me in seconds. So 20 times 3 times 60 times 60. If I do that on my calculator, I get 216,000 joules. So this car headlamp transforms 216,000 joules of energy in 3 hours. Okay, so that's part A. Now for part B, I want to find the resistance of this headlamp. So I know the resistance of it. I want to find the resistance of it, so I need an equation that's got R in it. I also know the power of it, and I also know the potential difference of it. So I need an equation that's got R, P, and V in it. Now if we go back and see what we saw before, saw the slide before, P is equal to V squared over R. So if I know the potential difference and I know the resistance, for example, then I can work out the power. In this case though, we actually know the power and we know the potential difference, we want the resistance. So I can rearrange this and get R equals V squared over P. So V was 10 volts. Now I'm squaring that, so I've got 10 squared divided by the power. Power again was 20. So that's equal to 100 divided by 20. So this is 5, and it's the resistance we're working out, so it has a resistance of 5 ohms. So really, when it comes to doing questions like this, all I need to do is look at what do I want to know, what 2 things do I want to work out, and then just choose the equation that I actually need in order to do that. Now there are kind of 2 applications that we need to think about in this case. The first one's very simple. When we know that when we pass a current through a conductor, often conductors get hot. So here we've got a kettle and the electricity comes in, and because this thing has a resistance, it gets hot. And actually, the power that's delivered to this thing depends upon its resistance. It depends on the current as well, but it depends on resistance. If this thing here didn't have a resistance, so in other words, if these electrons were able to travel through the wire without being stopped at all by these ions, if the resistance is 0, then no power would be delivered. So basically there would be no heat generated in here whatsoever. So this is often called I squared R heating. We don't necessarily need to know what it's called or whatever, but what we do need to know is that if something heats up, then we can calculate the power that is supplied to this thing. And if we want to know how much energy is kind of transferred into heat, then we can work out the power using I squared times R and multiply by the time that it takes, for example, this kettle to boil. So heating things up, if you want to know basically how much energy is delivered per second when you're heating things up, it depends upon the current and the resistance, and you just use that equation there. The second thing, and it mentions this in the specification, is specifically car motors. Now car starter motors need a large amount of power. Basically they have to get a really big engine moving in a small amount of time, so they need to deliver a lot of energy quickly. So car starter motors need a really big amount of power, and it's actually says that you need to know that in the specification. So we'll have a look at a typical sort of a very simple example again. So you've got a starter motor. It needs a power of 1.8 kilowatts to start the engine of a car. The potential difference from a car battery is 12 volts. Most car batteries now use 12 volts, and we want to know the current. So let's see exactly, so we can imagine that because we've got a big power and we've got a fairly small voltage, we're going to need a big current. So we just use our simple equation, P equals IV. I can rearrange that. I want to know the current, so that's equal to P over V, and then again I just put my numbers in. Well, 1.8 kilowatts is 1.8 times 10 to the 3, and the potential difference is 12, and if we work that out we get 150 amps. So car starter motors need a large amount of power, and to do this they have to deliver a really big current because the potential difference is really small. Now really, when it comes to solving any questions in an exam that have got to do with power and energy, it's basically just finding the right equation. So if we go back, for example, to this thing over here, these are all the equations you get given. You get given this equation here. You also get given this equation here. You get given that equation there, and you also get given that equation there. So really it's just a matter of looking through the question, seeing what quantities you've got, what quantities you need, and then just picking out the right equation. So that's it from me on power and energy, and thank you for listening, and I'll see you again soon.